We are surrounded by a cosmic ocean of stars and silent worlds. The question of alien life is no longer just science fiction. It is a scientific quest happening right now. Astronomers are scanning the galaxy, hunting for planets that could be homes for life. They look for worlds in the habitable zone, that sweet spot where water can flow as a liquid. They search for atmospheric biosignatures, the chemical fingerprints that life might leave behind. Today, we are embarking on a journey to 30 of the most promising alien worlds ever discovered. By the end, you will have a map to our galaxy's most likely addresses for life beyond Earth. We will visit a planet bathed in perpetual red twilight and another that might be a globe-spanning water world. Which of these distant points of light holds the secret we have always sought? Our journey begins right next door, cosmically speaking. A mere 4.2 light-years away, nestled in the faint glow of the star Proxima Centauri, orbits a world named Proxima Centauri b. This is the closest known exoplanet to Earth, a neighbor in the vast emptiness of space. It sits snugly within its star's habitable zone, that temperate region where temperatures might allow liquid water to exist on the surface. We believe it is a rocky planet similar in size to our own world, which immediately sparks the imagination. Could there be continents and oceans under that alien sun? But life here would face extraordinary challenges. Proxima Centauri is a red dwarf star, smaller and cooler than our sun, but notoriously temperamental. It frequently erupts with violent stellar flares, blasting the planet with intense radiation that could strip away any atmosphere and scald the surface. Another quirk of orbiting so close to a small star is that Proxima b is likely tidally locked. One side of the planet would be in permanent, scorching daylight, while the other is frozen in eternal night. This creates a stark and seemingly hostile environment. Yet hope is not lost. Scientists theorize that if Proxima b managed to retain a thick, protective atmosphere, heat could circulate from the day side to the night side. This could create a narrow, temperate band along the twilight line where conditions might be just right. Even more intriguing is the possibility of a global subsurface ocean, hidden beneath an icy crust, shielded from the stellar fury above. This makes Proxima Centauri be a paradox, a world of extreme threats and profound potential, and it stands as the #1 target for our future telescopes to study in unprecedented detail. But the search for life extends far beyond our closest stellar neighbor. A little over 40 light-years away, in the constellation of Aquarius, a small, cool star hosts one of the most extraordinary planetary systems ever discovered. This is the Trappist 1 system, a cosmic family of not one or two, but 7 rocky worlds, all roughly the size of Earth. They huddle close to their dim red dwarf star, completing their orbits in a matter of days. It is a compact, bustling solar system in miniature. Among this remarkable family, the 4th planet from the star, known as Trappist 1e, shines as the crown jewel. It sits perfectly within the star's habitable zone, a world where surface temperatures could be just right for liquid water. Unlike the extreme tidal locking of Proxima b, astronomers believe Trappist 1e might rotate slowly, giving it a more familiar day-night cycle. This raises the tantalizing possibility of a stable climate and weather patterns we could recognize. The true wonder of this system, however, is the opportunity it presents. Because all 7 planets orbit the same small star, our telescopes can study them as a set. Imagine having 7 Earth-sized worlds, each with a slightly different distance from its sun, lined up for direct comparison. With instruments like the James Webb Space Telescope, scientists can soon analyze the atmospheres of these planets one by one. They will look for the telltale signs of water vapor, methane, or oxygen. If life exists on one of these worlds, its atmospheric fingerprint could stand out starkly against the sterile signatures of its siblings. Trappist 1e is not just a single promising world. It is part of a celestial laboratory, offering us our best chance to understand how common or rare a living planet might be. While the TRAPPIST-1 system offers a family portrait of potential worlds, our search for life also honors the pioneers, the discoveries that first proved Earth was not unique. One such trailblazer is Kepler 186f, a planet over 500 light-years away in the constellation Cygnus. This world holds a special place in history. When it was confirmed in 2014, it became the very first planet we ever found that was both roughly the size of Earth and orbiting comfortably within its star's habitable zone. That single discovery changed everything. It transformed the idea of an Earth-like world from a theoretical hope into a confirmed reality. Kepler 186f orbits a star much cooler and redder than our Sun, a M dwarf, completing a full journey around it in about 130 Earth days. It is a slightly larger cousin to our own planet, with a radius about 10% bigger than Earth's. This small difference in size places it in a fascinating category. It could be a rocky super-Earth, perhaps with more active geology and a thicker atmosphere, or it might be a world dominated by a deep global ocean. The star it circles bathes the planet in a perpetual, dim crimson light. A sunset there would be a permanent feature of the sky. This different stellar environment forces us to think creatively about biology. Plants, if they exist, might have evolved to harvest the star's infrared light, potentially painting the landscape in shades of black or deep purple to absorb every possible photon. The longer year and cooler star mean the planet's climate and seasons would operate on a different rhythm than our own. Yet, the fundamental condition for life as we understand it, the possibility of liquid water on a solid surface, is met. Kepler 186f is more than just a candidate. It is a symbol, a proof of concept that planets like ours are scattered across the galaxy, waiting in the quiet orbits of countless stars. Yet the search for life demands we look beyond the dim red dwarfs to stars that mirror our own. 1,600 light-years away, in the constellation Cygnus, a star named Kepler 452 shines with a familiar yellow-white light. Orbiting this sun-like star is a world that captured headlines as Earth's bigger, older cousin, Kepler 452b. This planet is a super-Earth with a diameter about 50% larger than our own world. That size places it in a fascinating and uncertain category. It could be a massive rocky planet, a true super-Earth with continents and mountains on a grander scale. Or its larger size might mean it is shrouded in a thick, gaseous envelope, making it a mini Neptune, a world with no solid surface at all. The true nature of its composition remains one of the key mysteries surrounding this distant point of light. What we do know is profoundly compelling. Kepler 452b orbits its star in a 385-day year, almost identical to our own. It resides comfortably in the middle of its star's habitable zone, a place where liquid water could pool on a rocky surface. Most remarkably, this star system is ancient. Kepler 452 is about 6 billion years old, 1.5 billion years older than our Sun. This means its planet has spent an extraordinarily long time, billions upon billions of years, in that life-friendly zone. On Earth, it took roughly 1 billion years for the first simple life to emerge after the planet formed. If Kepler 452b is a rocky world, it has had more than enough time for life not only to spark but to evolve into complex, perhaps even intelligent forms. It is a world of profound patience, offering a glimpse of what our own planet might become given another few billion years of quiet stability. The possibility that we are looking at a mature, living world, one that has had ages to develop under a sun nearly identical to our own, is a thought that resonates with a deep and powerful hope. But the galaxy holds other red dwarf systems with their own unique stories. A mere 40 light-years away, circling a remarkably calm and ancient star called LHS 1140, two super-Earths present a different kind of promise. The inner world, LHS 1140b, is a standout candidate. It is about 1.7 times the size of Earth but carries a staggering 6.5 times the mass. This extraordinary density suggests it is not a gaseous mini-Neptune, but a true mega-Earth, a rocky planet with a massive iron core and possibly a substantial atmosphere clinging to its powerful gravity. It orbits within its star's habitable zone, and the recent gaze of the James Webb Space Telescope has brought breathtaking news. Early data hints that LHS 1140b's atmosphere might be rich in nitrogen, the dominant gas in our own skies. This is a thrilling clue, as a stable nitrogen atmosphere is a key ingredient for a temperate, potentially life-friendly world, acting as a buffer against harmful radiation. It transforms this dense planet from a statistical oddity into a frontrunner in the search. Its sibling, LHS 1140c, orbits farther out in a cooler, more distant path. While likely too cold for surface oceans as we know them, its presence completes the picture of a complex planetary family around a stable, old star. This system reminds us that habitability comes in many forms, and a dense, iron-rich world under a nitrogen sky might be just as welcoming as a twin of our own pale blue dot. A stable, quiet star can make all the difference. 100 light-years away, the red dwarf TOI 700 shines with a gentle consistency, free from the violent flares that plague so many of its kind. Around this peaceful sun orbits a remarkable family of at least 4 small, rocky worlds, and 3 of them hold special promise for life. The third planet out, TOI 700d, is a true Earth twin in size, orbiting squarely in the middle of the star's habitable zone. Its year lasts just 37 days, and because the star is so calm, this world has likely enjoyed billions of years of stable conditions. Computer models suggest it could be a water world, completely covered by a global ocean with a thick, carbon dioxide-rich atmosphere, or perhaps a more familiar mix of land and water. This combination of Earth-like size, a perfect orbital position, and a tranquil star makes TOI 700d one of the highest priority targets for the James Webb Space Telescope to search for atmospheric biosignatures. But the system's riches do not end there. Astronomers recently confirmed TOI 700e, another Earth-sized planet that orbits even closer to the star, nestled in what scientists call the optimistic habitable zone. This region extends the possibilities where a planet with a thick enough atmosphere or the right greenhouse effect could still maintain liquid water. The presence of both D and E suggests a system brimming with temperate real estate. Further out, we find TOI 700f, a potentially rocky world on the colder, outer edge of the habitable zone. While it might be an icy world, it completes a stunning picture of a single, quiet star hosting multiple planets where conditions could be just right for life, each offering a different experiment in planetary climate and chemistry. The quiet stability of a single star is not the only recipe for a habitable world. Some of the most promising planets exist in complex stellar families. 23 light-years from Earth, in the constellation Scorpius, the planet GJ 667cc orbits within a remarkable triple-star system. This super-Earth, about 4.5 times the mass of our planet, circles its primary star, a dim red dwarf, in just 28 Earth days. That orbit would be blisteringly close to a star like our Sun, but because this star is so faint and cool, the planet actually receives a very similar amount of light and heat as Earth does. It sits right in the heart of its star's habitable zone, a true Goldilocks world by that crucial measure. The true wonder, however, is the sky above it. The planet's primary red dwarf is itself locked in a tight dance with 2 other stars, both orange dwarfs, that orbit each other farther out. From the surface of GJ 667cc, the primary star would appear large and dim in the sky. But the 2 companion stars would shine in the distance like a pair of brilliant, permanent moons, casting soft, additional light. During a sunset, you might see the main red sun dip below the horizon while the twin orange suns remain glowing in the twilight. This celestial ballet raises fascinating questions about climate stability. While multi-star systems can create chaotic orbits, GJ6667cc's path around its primary star appears stable, protected by the vast distance to the other two stars. This means it could enjoy a consistent climate for billions of years, despite the complex gravitational dance happening around it. It is a powerful reminder that life, if it exists, might find a way under the light of not one but three suns. Our galaxy's definition of a habitable world is far broader than we once imagined. Beyond the familiar rocky planets, a new and exotic class of world has emerged as a potential cradle for life. Enter K218b, a planet orbiting a cool dwarf star about 120 light-years away. This is not a super-Earth, it is a mini-Neptune, a world over 8 times the mass of our own, likely shrouded in a thick, hydrogen-rich atmosphere. For years, such planets were written off as gas-shrouded hellscapes, far too hot and pressurized for any familiar biology. But recent discoveries have turned that assumption on its head. K218b sits within its star's habitable zone, and its size and density suggest a breathtaking possibility beneath that gassy veil. Scientists now theorize it could be a Haitian world, a term blending hydrogen and ocean. The picture is one of profound alien beauty. Imagine a planet with no solid surface as we know it. Instead, beneath a vast, warm, and hazy hydrogen sky, there lies a planet-wide ocean, a deep, global sea that could stretch from the upper atmosphere all the way down to a crushing, high-pressure ice layer or a rocky core. This is a water world on a scale that dwarfs our own, an entire planet baptized in a single, endless ocean. The true breakthrough came when the James Webb Space Telescope turned its gaze toward K218b. By analyzing the starlight filtering through the planet's atmosphere, Webb detected the clear signatures of carbon dioxide and methane. This is a monumental finding. On a rocky planet, this combination could hint at geological activity or even biology. On a Haitian world, it suggests active chemistry happening within or above that global ocean. But the most electrifying and hotly debated clue was a tentative signal of something else, dimethyl sulfide. On Earth, dimethyl sulfide is almost exclusively produced by marine phytoplankton, tiny living organisms in our seas. Its detection in the atmosphere of K218b is for now unconfirmed and requires further study, but the mere possibility sends a shockwave through the field of astrobiology. It means we must now seriously consider that life could not only exist but potentially thrive in the warm, dark oceans of a gassy, water-dominated world utterly unlike our own. K218b has shattered the old rules, forcing us to expand our search for life into entirely new and unexpected environments. The idea of a Haitian world forces us to rethink the very definition of a habitable planet. These are not places with familiar shorelines or continents. Instead, picture a planet where the sky is a perpetual, warm haze of hydrogen, pressing down on a dark, globe-spanning ocean that could be tens or even hundreds of miles deep. Beneath that immense atmospheric blanket, the surface pressure would be crushing and temperatures could be hot, perhaps even reaching the boiling point of water. Yet, counterintuitively, the ocean itself would remain liquid, kept from evaporating entirely by the sheer weight of the atmosphere above it. This creates a stable, if extreme, aquatic environment that could persist for billions of years. The chemistry within such an ocean could be rich and complex. Organic molecules, the building blocks of life, might form readily in the interplay between the hydrogen-rich atmosphere and the water below, or they could well up from hydrothermal vents on a hidden seafloor. Life here would not need sunlight at all. It could thrive on chemical energy in the eternal darkness, much like the ecosystems around deep-sea vents on Earth. This expands the search dramatically. Because a Hycean world's warmth comes as much from its own internal heat and atmospheric pressure as from its star, such planets could exist much farther from their suns, in what we would normally consider the frozen outer reaches of a solar system. They redefine the boundaries of where we should look, and there is a practical, thrilling advantage for astronomers. These planets are large and puffy, with expansive atmospheres that are far easier for our telescopes to peer into. When the James Webb Space Telescope observes a transit where a planet passes in front of its star, it analyzes the starlight filtering through the planet's air. A thick, extended atmosphere like that of a Hycean world gives the telescope a bigger, clearer signal to work with. It is like trying to study the composition of a fog bank versus a thin wisp of mist. This makes Hycean planets prime targets for detecting biosignature gases, such as dimethyl sulfide or other complex molecules that might hint at biological activity. K2-18b was just the beginning. Its discovery has opened an entirely new chapter, suggesting that some of the best places to find life might not be Earth twins at all, but these strange, dark, and deeply alien water worlds. A silent neighbor holds a profound secret. Just 12 light-years away, one of the smallest and faintest stars we know, Teegarden Star, is home to a planet that nearly matches Earth's own mass. This is Teegarden Star B, a world so lightweight it barely tugs on its dim parent sun, yet it orbits perfectly within the star's narrow habitable zone. Its year is a mere 4.9 Earth days, a frantic sprint around a star so cool its light is a deep infrared crimson. Standing on the surface of this world, the sun would appear as a dull, cherry-red ember in a sky of perpetual twilight, casting long, weak shadows across an alien landscape. The dimness brings a strange stability. Without the energetic outbursts common to many red dwarfs, Teegarden Star offers its planets a chance for a calm, uninterrupted existence over billions of years. But this proximity creates another fascinating possibility: tidal heating. Just as Jupiter's gravity stretches and squeezes the volcanic moon Io, the star's gravitational pull could be flexing the very rock of Teegarden Star B, generating internal warmth from deep within its core. This hidden furnace could power volcanic activity or maintain a subsurface ocean beneath a frozen crust, creating a warm, liquid sanctuary completely independent of the faint sunlight above. For life, this internal heat could be a saving grace, a second source of energy in a system where the primary star provides only a feeble glow. The combination of an Earth-like mass, a stable orbit in the habitable zone, and the potential for tidal heating makes this faint, nearby world a silent and deeply compelling candidate in our cosmic search. Yet our search for life must also consider its opposite, the cautionary tales of worlds that crossed a fatal line. Just 12 light-years away, a quiet red dwarf named GJ1061 hosts a compact system of at least 4 small, rocky planets. 2 of these worlds, GJ1061c and D, are especially revealing. They are both roughly Earth's mass, siblings formed from the same material around the same gentle star, but their fates likely diverge dramatically. Planet C orbits closer to its sun, skirting the very inner edge of what we might optimistically call the habitable zone. This position is perilously close to the fire. With just a slightly thicker atmosphere or a bit more stellar heat, this world could have experienced a runaway greenhouse effect. Here is how that disaster unfolds. Imagine a planet where rising temperatures cause more water to evaporate from its oceans. Water vapor is itself a powerful greenhouse gas, trapping even more heat, which evaporates more water in a terrifying feedback loop with no natural break. The entire ocean could eventually boil away into space, leaving behind a scorched, bone-dry world shrouded in a thick, choking atmosphere of carbon dioxide, a true Venus-like hellscape. GJ1061c may stand as a solemn monument to this process, a world that once had potential but now lies eternally silent and searing hot. Its sibling, Planet D, tells a different story. Orbiting a bit farther out, it sits more comfortably within the star's temperate habitable zone. Here, the same delicate balance between atmosphere, water, and sunlight might have been maintained. The two planets, so similar in size and origin, present us with a perfect natural experiment. By studying them as a pair, astronomers can ask profound questions. What tiny initial difference sealed their separate fates? Was it the precise amount of water they formed with, the thickness of their early atmospheres, or the timing of volcanic activity? The GJ1061 system offers a rare opportunity to observe the fine line between a living world and a dead one, to understand how a planet's climate can tip from paradise into inferno. It reminds us that habitability is not a permanent state, but a fragile and dynamic condition, one that must be nurtured and maintained across the eons. This fine line between life and desolation makes every new discovery a cause for celebration and intense scrutiny. A mere 31 light-years from Earth, a quiet red dwarf named Wolf 1069 hosts a world that has astronomers buzzing with excitement. Wolf 1069b is a recent and remarkable find, a planet with almost exactly the same mass as Earth. It completes an orbit around its dim, calm star in just 15.6 Earth days, placing it squarely in what scientists call the conservative habitable zone. This is the most reliable part of the temperature band, where a planet with an Earth-like atmosphere has the strongest chance of maintaining stable liquid water on its surface. Like many worlds orbiting such faint stars, Wolf 1069b is almost certainly tidally locked. One hemisphere basks in permanent daylight, while the other is frozen in endless night. This creates a dramatic and challenging environment, but not necessarily a hopeless one. Advanced climate models suggest that if this planet has managed to hold onto a reasonably thick atmosphere, something similar to our own, the winds would act as a planetary life support system. They would carry heat from the scorching day side across the terminator, the twilight line, and into the frigid darkness of the night side. This circulation could prevent the atmosphere from freezing out entirely and, crucially, could create a region of just right temperatures along that eternal dawn or dusk zone. Here, in a band of perpetual sunrise or sunset, liquid water could pool on the surface. Furthermore, because Wolf 1069b is a rocky world of Earth's mass, there is a strong possibility it has an active, molten iron core that generates a protective magnetic field. This planetary shield would be vital, deflecting the charged particles from its red dwarf star and preventing those particles from stripping away the very atmosphere that makes its temperate climate possible. Wolf 1069b represents a new archetype in our search, a quiet Earth mass world with all the right ingredients for habitability quietly ticking along in our cosmic backyard, waiting for our telescopes to learn its secrets. The quiet stability of nearby stars is mirrored by discoveries from our first great planet hunting mission. Over 1,000 light-years away, the Kepler Space Telescope revealed a pair of worlds that redefined our expectations. Orbiting the ancient orange star Kepler-62 are two remarkable super-Earths, Kepler-62e and Kepler-62f. Both planets are larger than our own, with E being about 1.5 times Earth size and F being just 10% bigger, making it one of the most Earth-sized planets known in a habitable zone. They orbit a star that is cooler, smaller, and older than our Sun, completing their years in 122 and 267 days respectively. This places them comfortably within their star's temperate band, but their true nature is a subject of captivating speculation. Given their size and position, many astronomers believe these are not rocky worlds like Earth, but water worlds. They could be completely shrouded in deep, global oceans with no land in sight. Imagine a planet where the only horizon is an endless, rolling sea under a dim orange sun. The pressure at the bottom of such an ocean would be immense, creating exotic forms of ice not from cold, but from crushing force, a solid seafloor of hot ice. Yet, in the sunlit upper layers, life could find a way, perhaps floating in vast, planet-wide algal blooms or thriving in complex aquatic ecosystems. These worlds showed us that a habitable zone could host planets utterly alien in their composition, expanding the canvas of possibility. Around the same time, Kepler introduced us to a world that hinted at a more familiar scale. Kepler 69c orbits a star remarkably similar to our own Sun, a yellow dwarf about 80% as luminous. This super-Earth, about 70% larger than our planet, completes an orbit every 242 days, placing it near the inner edge of its star's habitable zone. When it was discovered, it was celebrated as one of the first potentially habitable planets found around a Sun-like star, a milestone that captured the public imagination. However, subsequent study revealed a more complex and cautionary story. Kepler 69c receives about 40% more stellar flux than Earth does, a significant increase. This places it in a precarious position, potentially making it more of a super-Venus than a super-Earth, a world where a runaway greenhouse effect may have long ago boiled away any oceans. Its exact nature remains uncertain, a reminder that location alone does not guarantee a welcoming climate. Together, these three Kepler pioneers, the enigmatic water worlds of the 62 system and the solar twin candidate of 69c, formed a crucial bridge in our understanding. They were the vanguard, the early maps that proved habitable zones around diverse stars were not empty. They showed us the diversity of forms these worlds could take, from globe-spanning oceans to scorching near twins of Earth, and in doing so, they paved the direct path for the more refined and targeted searches we conduct today. The quiet stability of a star is a precious gift for any orbiting world. 42 light-years away in the constellation Pictor, a star named HD 40307 offers just that. This orange dwarf is older and calmer than our Sun, a steady hearth in the cosmic dark. Orbiting this reliable star is a fascinating enigma, a planet designated HD 40307g. This world is a super-Earth with a mass at least 7 times that of our own planet. Its orbit lasts about 200 Earth days, placing it squarely in the middle of its star's habitable zone. That longer orbital period is a key detail, because it is not hugging its star as closely as many other habitable zone planets. It likely experiences far less extreme tidal forces. This could mean it rotates more freely, possibly even having a day-night cycle similar to Earth's, avoiding the fate of permanent tidal locking. But the true mystery of HD 40307g lies in its very nature. With its substantial mass, astronomers are locked in a debate. Is this a true super-Earth, a massive rocky planet with towering mountains and deep metal cores? Or is it a mini-Neptune, a world with a small rocky heart smothered under a deep, gaseous shroud of hydrogen and helium? The answer dictates everything about its potential for life. If it is a rocky super-Earth, its stronger gravity could hold onto a thick, protective atmosphere, potentially creating a stable and temperate climate under its orange sun. If it leans toward the mini-Neptune model, the story shifts dramatically. In that case, the immense pressure and heat beneath its gaseous envelope might create conditions for a Hycean world, a global ocean of liquid water trapped beneath the clouds. HD 40307g is a reminder that a promising location is only the first clue. The architecture of the world itself holds the final answer to whether it is a new Earth or a profoundly alien sea, both possibilities equally mesmerizing in their potential. 11 light-years from Earth, a world of gentle possibilities awaits. Ross 128b is an Earth-sized planet, a quiet neighbor orbiting an exceptionally quiet star. Its red dwarf host, Ross 128, is a stellar rarity, a star that shows almost no signs of the violent flares and eruptions that plague most of its kind. This profound calm cannot be overstated. For a planet so close to its sun, a mere 20-day orbit, This stellar serenity is the difference between a potential paradise and a radioactive wasteland. It means Ross 128b has likely enjoyed billions of years of uninterrupted climate evolution, free from the atmospheric stripping tantrums that could doom other worlds. The planet receives about 38% more stellar radiation than Earth, but because its star is so much cooler, this energy is mostly in the form of infrared heat. This places it on the warmer inner edge of the habitable zone, a world that might feel more like a global tropical greenhouse than a temperate Earth. Yet, like many close-orbiting red dwarf planets, it is almost certainly tidally locked. One face is bathed in permanent, warm daylight, while the other is an eternal, frozen night. The key to its habitability lies in that stark division. If Ross 128b possesses a reasonably thick atmosphere, models show that powerful global winds would act as a planetary circulatory system. These winds would ferry heat from the scorching day side across the twilight terminator and into the deep freeze of the night side. This constant motion could prevent the atmosphere from freezing solid on the dark side and, crucially, could create a vast region of just right temperatures along the entire rim of the planet. In this band of perpetual sunrise or sunset, under a dim, reddish sun fixed forever on the horizon, liquid water could flow and pool. The planet's Earth-like size increases the odds it has a protective magnetic field, further shielding its atmosphere from even the gentle stellar wind of its quiet star. Ross 128b represents a best-case scenario for life around the galaxy's most common star type, a stable, temperate world where the greatest violence is not from the sky, but perhaps from the weather moving across its eternal dawn. The serene possibility of Ross 128b stands in stark contrast to one of astronomy's most compelling mysteries. 20 light-years away, the red dwarf star Gliese 581 became the center of a firestorm with the reported discovery of a planet called GJ 581g. Announced in 2010, the data suggested a world of profound significance. With a mass just 3 to 4 times that of Earth, it appeared to be a solid, rocky super-Earth. More importantly, its calculated orbit placed it perfectly in the middle of its star's narrow habitable zone, a true Goldilocks world in every sense. The potential was breathtaking. Here was a planet that could have a stable climate, liquid water, and all the basic ingredients for life, orbiting a quiet star right in our galactic neighborhood. For a moment, it seemed we had found one of the best candidates yet for an Earth-like world. But science thrives on skepticism, and the story of GJ 581g took a dramatic turn. Other teams of astronomers, using the same initial data and new observations, began to question the planet's very existence. They proposed that the subtle wobble in the star's light, the signal interpreted as the gravitational tug of planet G, might not be from a planet at all. Instead, it could be an artifact of the star's own natural activity. Red dwarf stars like Gliese 581 are often covered in star spots, similar to sunspots but larger and more persistent. As the star rotates, these dark and bright patches on its surface can create a rhythmic pattern in its light that mimics the signal of an orbiting planet. Distinguishing between a star's heartbeat and a planet's gentle pull is one of the greatest technical challenges in exoplanet science. The debate over GJ 581g became a classic case study in the rigorous process of discovery. A single intriguing signal is not enough. It must be verified and re-verified, observed with different instruments, and analyzed by independent teams to rule out every other possible explanation. For over a decade, the status of Planet G has remained in limbo, officially unconfirmed. This controversy is not a failure of science but a demonstration of its strength. It shows the meticulous care required before we can truly claim to have found a new world, especially one as promising as a habitable super-Earth. The ghost of GJ 581g serves as a crucial reminder. In our excitement to map the cosmos, we must let the evidence lead, even when it points away from our most hopeful discoveries. The controversy over a single planet's existence underscores the incredible precision required in this cosmic hunt. Yet, just 16 light-years away, we find a system that offers not one, but two confirmed Earth mass worlds with no such ambiguity. The star JJ1002 is an ultra-cool dwarf, a star so faint and diminutive it blurs the line between a true star and a large, failed star known as a brown dwarf. Its light is a deep, infrared whisper. Orbiting this faint ember are two rocky planets, JJ1002b and C, both almost exactly the mass of our own world. Planet B completes an orbit in just 10 days, placing it on the warmer inner edge of the star's habitable zone. Planet C, with a 21-day year, sits farther out in a cooler, more temperate position. Because their star provides so little heat, both planets must huddle extremely close to it to stay warm enough for liquid water, like children gathered near a dying campfire. This proximity likely means they are tidally locked, presenting the now familiar challenge of a permanent dayside and nightside. However, the profound calm of their ultra-cool dwarf star is a monumental advantage. Such stars are not just quiet, they are virtually inert, offering stability measured in trillions of years. This gives life an unimaginable amount of time to emerge and evolve in an environment free from stellar tantrums. Studying these planets, however, pushes our technology to its absolute limit. Their star is so dim that detecting the planets at all was a feat of modern astronomy. Analyzing their potential atmospheres with current telescopes is even more difficult, as the signal from such a faint star and its small worlds is incredibly weak. Yet, their discovery proves that Earth-mass planets are common around the smallest, most numerous stars in the galaxy, vastly expanding the number of possible addresses for life. This principle of multiple worlds extends to our very closest stellar neighbor. Remember Proxima Centauri b, that promising yet challenging world bathed in red light. It is not alone. Astronomers have confirmed a third planet in that system, Proxima Centauri d. This inner world is far lighter than its siblings, a sub-Earth with a mass only about a quarter of our planet's. It whips around its star in a blistering 5-day orbit, far too close to be in the habitable zone. The surface would be scorching, likely a molten landscape under the constant flare of its active star. So why does this tiny, hot world matter in our search for life? Its existence completes a profound picture. It shows that even a single, modest red dwarf star can build a complex planetary family with a variety of worlds, from a small, rocky inferno like Planet D to a temperate, Earth mass candidate like Planet B. Each planet in such a system tells a part of the story of how that system formed and evolved. The presence of multiple planets also increases the chances that materials essential for life, like water and organic compounds, could have been shared between them through impacts or gravitational interactions early in the system's history. Proxima Centauri d reminds us that habitable worlds are not isolated accidents. They are often part of a rich planetary community, and understanding the entire family, from the smallest sibling to the most promising cousin, is key to understanding whether any of them could truly be a home. The quiet, enduring legacy of a telescope continues to bear fruit long after its mission ended. While the Kepler Space Telescope ceased primary operations, its mountain of data remains a goldmine, yielding new gems with every sophisticated reanalysis. Among these late-rising stars is Kepler 1649c, a world that stands out for its striking familiarity. When astronomers combed through old Kepler data with new algorithms, they found this planet, and the numbers were startling. Kepler 1649c is almost exactly the same size as Earth, with a radius just 6% larger. It orbits a small, cool red dwarf star, receiving about 75% of the starlight that Earth gets from our Sun. This places it firmly within its star's habitable zone, a temperate orbit where an Earth-like atmosphere could support liquid water. It is one of the closest matches to our own world in both size and stellar heating ever found in the Kepler data, a true Earth analog hiding in plain sight. Its year is just 19.5 Earth days, a reminder of how close it must orbit its faint sun to stay warm. While likely tidally locked, its Earth-like proportions make it a prime candidate for a stable atmosphere and a possible magnetic field, elevating it as a key target for future atmospheric studies. Kepler 1649c is not alone in this posthumous bounty. Other re-examined data points have revealed similar treasures like Kepler 1229b. This super-Earth is about 40% larger than our planet and orbits a red dwarf, completing a full circle in 86 days. Its orbit is special, placing it right in the middle of its star's conservative habitable zone, the sweetest spot for potential liquid water. Another, Kepler 1638b, tells a similar story. It is a rocky world roughly 1.5 times the size of Earth, found orbiting comfortably within its own red dwarf's habitable zone. These are not flukes. They represent the vast population of small, rocky worlds that Kepler statistically proved fill our galaxy. For every one like Kepler 1649c that we painstakingly confirm, there are likely thousands more waiting in the data, their subtle signals still blended with stellar noise. These later discoveries underscore a profound truth. Kepler's primary mission was not just to find individual planets, but to conduct a cosmic census. Its legacy is the statistical certainty that planets, especially Earth-sized and super-Earth planets in habitable zones, are common around red dwarf stars, which themselves make up over 70% of the stars in the Milky Way. This means the raw material for life, in terms of suitable real estate, is scattered almost everywhere we look. Each new candidate pulled from the archive, like these three, adds another day to point to a revolutionary map, one that increasingly suggests our galaxy is not a barren desert, but a neighborhood rich with silent, waiting worlds. This galactic census points us towards specific worlds where the ocean, not the land, might hold the key. Among these, a planet called TOI 1452b stands out as a prime example. Orbiting a red dwarf star about 100 light-years away, this super-Earth is roughly 70% larger than our world and about 5 times as massive. That unusual density tells a fascinating story. While it could be a rocky planet with an immense iron core, many astronomers studying the data favor a more captivating possibility. They believe TOI 1452b is likely a true water world, not just damp but absolutely drenched. The best models suggest it could be covered by a deep, global ocean, a layer of water so vast it might make up as much as 30% of the planet's total mass. For comparison, Earth's oceans, for all their depth, constitute less than 1% of our planet's mass. The entire surface of this alien world could be a single, uninterrupted sea, hundreds of miles deep under a thick, steamy atmosphere. At the bottom, the pressure would be so immense that water would form exotic high-pressure ices, creating a solid seafloor of hot ice Roman 7, a form of water ice that exists only under crushing force. Yet, in the sunlit upper layers, this endless ocean could be a perfect nursery for life, a stable, aquatic environment that has persisted for billions of years. While some worlds are defined by their water, others earn their place through perfect positioning. A mere 100 light-years away, a star known as LP 899 hosts a remarkable pair of super-Earths. The outer world, LP 899c, is a recent and thrilling discovery. It is about 40% larger than Earth and orbits its cool red dwarf star in just over 8.5 Earth days. That incredibly short year places it squarely in the middle of the star's habitable zone. What makes this planet particularly compelling is the nature of its sun. LP 899 is an exceptionally quiet and cool star, even for a red dwarf. This stellar calm dramatically increases the chances that Planet C has held onto a substantial atmosphere over its long lifetime, protected from the eroding winds that plague more active stars. Its size suggests it is almost certainly a rocky world, and its location offers the possibility of a stable, temperate climate. Because it is so close to us and transits its star from our viewpoint, the James Webb Space Telescope can readily analyze its atmosphere. LP-899c has swiftly risen to become one of the top-ranked targets in the entire search for life beyond our solar system, a new favorite holding immense promise. Our final stop returns us to a familiar celestial family, the extraordinary TRAPPIST-1 system. We have already met the promising world TRAPPIST-1e, but the system's outer reaches hold another candidate. TRAPPIST-1g is the sixth planet from its tiny star, an Earth-sized world with an orbit of about 12 Earth days. It receives significantly less stellar energy than its sibling, placing it on the colder outer edge of the habitable zone. On its own, this might suggest a frozen, icy globe. Yet, planetary science offers a pathway to warmth. If TRAPPIST-1g possesses a thick atmosphere rich in greenhouse gases like carbon dioxide or methane, that atmospheric blanket could trap enough of its star's feeble heat to create a temperate surface. This is not mere speculation. In our own solar system, we see a clear analog. Mars is a small, frozen desert with a thin atmosphere. But scientists strongly suspect that in its distant past, Mars was warmer and wetter, with a thicker carbon dioxide atmosphere that created a greenhouse effect capable of sustaining rivers and lakes. TRAPPIST-1g, being larger and more massive than Mars, would have a much stronger gravitational grip, making it far easier to retain just such a thick, climate-modifying atmosphere. It represents a different kind of habitable possibility, one where the planet's own air acts as a furnace, turning a distant orbit into a potential refuge. The outer reaches of our own solar system already challenge the narrow definition of a habitable world. While we scan distant stars for Earth twins, profound mysteries with the potential for alien life exist right here, orbiting Jupiter and Saturn. These are not planets basking in a sun's warmth, but frozen moons hiding secret oceans. Jupiter's moon Europa, for instance, is a world encased in a global shell of ice crisscrossed by cracks and ridges. But beneath that frozen crust, strong evidence points to a vast, salty ocean, kept liquid by the relentless gravitational squeezing of Jupiter itself. This subsurface sea could contain more than twice the water of all Earth's oceans combined, a dark, pressurized abyss that has persisted for billions of years. Here, life would not rely on sunlight, but on chemical energy welling up from hydrothermal vents on the ocean floor, just as it does in Earth's deepest, darkest trenches. The plumes of water vapor erupting from Saturn's moon Enceladus offer even more direct evidence, spraying samples of its hidden ocean into space, where our spacecraft have detected organic molecules and salts within the icy particles. These are not planets in any classical habitable zone, yet they possess all the fundamental ingredients for life: liquid water, chemistry, and a stable, long-lived source of energy. Saturn's largest moon, Titan, presents a vision of habitability that is utterly alien. It is a world shrouded in a thick, orange haze with rivers and lakes etching its surface. But these are not waterways as we know them. On Titan, with surface temperatures plunging to -290 degrees Fahrenheit, the liquid is not water but methane and ethane. This creates a hydrocarbon cycle eerily similar to Earth's water cycle, with rain, flowing rivers, and great seas of liquid natural gas. Could life exist in such a frigid chemical soup? If it does, it would be built on a fundamentally different biochemistry, one that uses liquid methane as a solvent instead of water. Such life would be slow, strange, and almost unimaginable to us, but its possibility forces us to reconsider the very foundations of biology. The ingredients for complex organic molecules are abundant in Titan's atmosphere and on its surface, suggesting that the probiotic chemistry that led to life on Earth is actively at play in this deep freeze. Even closer to home, in a place seemingly inhospitable, another possibility floats. The cloud decks of Venus, our neighboring planet, present a paradox. The surface is a crushing, lead-melting hellscape, but about 30 miles up, the temperature and pressure are startlingly Earth-like. Within this temperate layer of sulfuric acid clouds, some scientists have proposed a startling idea. Microbial life, adapted to high acidity, could potentially float there, harvesting energy from sunlight or chemical reactions in the atmosphere. The tentative detection of phosphine gas, a molecule often associated with biological activity on Earth, has sparked intense debate and renewed interest in our closest planetary neighbor. Venus reminds us that a planet's surface can be a tomb while its skies might hold a sanctuary. All of these examples, from the subsurface oceans of icy moons to the hydrocarbon lakes and acidic clouds, point to a single, transformative conclusion. Our search for life must break free from the constraint of the traditional habitable zone, that narrow band around a star where liquid water can exist on a rocky surface. That zone is a useful starting point, a guidepost built from the only example of life we know, but it is not a boundary. Habitability is not a location, it is a condition. It exists wherever a stable liquid medium, a source of energy, and the right chemistry persist long enough for complexity to arise. The galaxy is likely filled with such environments in forms we are only beginning to imagine, hidden in the dark, the cold, and the chemically exotic. To find life, we must learn to look for the processes, not just the places. Discovering these silent worlds across the void requires a special kind of cosmic detective work. We cannot see them directly with our telescopes, not yet. Instead, astronomers must observe the subtle, telltale clues they leave behind on their parent stars. Two primary methods have unlocked this new era of discovery. The first is the transit method. Imagine a planet like a tiny insect passing directly in front of its much larger star from our point of view. As it transits, it blocks a minuscule fraction of the star's light, causing a predictable, repeating dip in brightness. Sophisticated telescopes like Kepler and TESS stare at thousands of stars, patiently waiting for these faint winks. From the depth and timing of the dip, scientists can calculate the planet's size and the length of its year. The second method is radial velocity, or the wobble technique. A planet does not simply orbit a star. The star and planet both orbit a common center of mass, causing the star itself to wobble in a tiny, rhythmic dance. This motion shifts the star's light very slightly toward the blue end of the spectrum as it moves toward us, and toward the red as it moves away. By measuring this stellar wobble with incredibly precise instruments, astronomers can determine the planet's mass and the shape of its orbit. Often, these two methods work in tandem. A transit reveals a planet's size, and radial velocity measurements confirm its mass. Together, they tell us the planet's density, the critical clue that tells us if we are looking at a puffy gas giant, a dense rocky world, or a global ocean planet. But knowing a planet exists is only the beginning. The true revolution is understanding what its environment is like, and for that we have a new, unparalleled tool. The James Webb Space Telescope is changing everything. When a planet transits its star, a tiny fraction of the star's light filters through the planet's atmosphere on its way to us. Different gases in that atmosphere absorb specific colors or wavelengths of that starlight. Webb's powerful infrared eyes are designed to catch this filtered light and spread it out into a detailed spectrum, a chemical barcode of the alien sky. By reading this barcode, scientists can sniff out the presence of water vapor, carbon dioxide, methane, and even more complex molecules. The dream is to find a combination of gases that should not exist together in a stable atmosphere without something actively replenishing them, a potential biosignature. On Earth, the abundant oxygen in our air is a direct product of life, constantly replenished by plants and phytoplankton. Finding oxygen alongside methane, which reacts quickly and destroys oxygen, in an exoplanet's atmosphere would be a tantalizing, though not definitive, hint of biological activity. Webb is now turning these theoretical searches into reality, taking the first tentative sniffs of atmospheres around worlds like K218b and Trappist 1e. It is our most powerful instrument yet for answering the oldest question, transforming distant points of light into worlds with weather, chemistry, and perhaps, just perhaps, a breath of something extraordinary. This silent abundance of worlds presents us with a profound and unsettling contradiction. If the galaxy is so rich with potential homes for life, why does the cosmos feel so profoundly empty? This is the heart of the Fermi paradox, a simple question with universe-shaking implications. Where is everybody? Enrico Fermi, the brilliant physicist, posed it over lunch one day in 1950. Given the age and vast size of the galaxy, even if intelligent life were exceedingly rare, it should have had ample time to arise somewhere and spread, filling the Milky Way with its presence. We should see evidence of great cosmic engineering, signals crisscrossing the void, or perhaps even visitors, yet we detect nothing but silence and starlight. This deafening quiet suggests something is preventing life from reaching the stars, a concept scientists call the Great Filter. Imagine a series of immense, difficult steps on the path from a sterile planet to a spacefaring civilization. The Great Filter is the one step that is almost impossibly hard to pass. It could be a single, catastrophic event or a whole series of unlikely breakthroughs. The terrifying question is, where does this filter lie? Is it behind us in our distant past? If so, we are miraculously lucky. Perhaps the origin of life itself from non-living chemistry is the filter, an event so staggeringly improbable that we are the only ones in our galactic neighborhood to have won that cosmic lottery. Or perhaps the filter is the leap from simple, single-celled life to complex, multicellular organisms, a transition that took over 2 billion years on Earth. If these early hurdles are the Great Filter, then the silence makes a tragic kind of sense. Life is a rare spark that almost always flickers out before it can truly catch fire. The planets we have listed would then be mostly beautiful, barren hopes, worlds where the chemistry is right but the spark never came. But there is a far more unsettling possibility. What if the Great Filter is not behind us but ahead? What if the step from an intelligent, technological civilization to a long-lived, interstellar one is the one that is nearly impossible to clear? This filter could take many forms. It might be the inevitable self-destruction that comes with advanced technology, through nuclear war, engineered pandemics, or runaway artificial intelligence. It could be a cosmic catastrophe we have yet to encounter, like a gamma ray burst sterilizing planets on a galactic scale. Or it could be a simple, disheartening reality that interstellar travel is physically or economically impossible for any civilization, forever trapping intelligent beings in their own solar systems. If this is the case, then our discovery of so many habitable worlds is not a promise but a warning. It means the galaxy is a graveyard of civilizations that rose, looked to the stars, and then vanished, each leaving behind only the silent chemistry of their once living worlds. Our search for biosignatures in the atmospheres of planets like Trappist 1e or K218b is now a search for clues to this ultimate mystery. Finding simple microbial life on another world would be the most monumental discovery in human history, but it would also carry a chilling message. If life is common but we find no evidence of intelligence, it strongly suggests the Great Filter lies ahead, waiting for us in our future. Finding nothing but sterile worlds, however, might indicate the filter is in the past and we are a glorious, lonely accident. Either answer is humbling. This paradox adds a layer of profound depth and urgency to our catalogue of 30 promising planets. We are not just making a list of addresses. We are searching for our own place in a cosmic story, trying to determine if we are the first chapter, the last, or a solitary sentence in an otherwise empty book. The silence is not an absence of data. It is the question we are trying to answer with every new world we find. The silence we perceive is not a wall but a veil. To lift it, we need new eyes, instruments of such power they will transform those distant points of light into actual pictures. The next decade will bring a revolution in our vision, beginning right here on the ground. Projects like the extremely large telescope in Chile and the giant Magellan telescope are not just upgrades. They are behemoths with mirrors spanning the width of a tennis court, gathering so much light they will begin to directly image some of the larger exoplanets we have catalogued. We will see them not as dots but as tiny, distinct specks of light next to their stars, allowing us to analyze their atmospheric spectra in far greater detail. But to find true Earth twins, we must go to space and block out the stellar glare entirely. That is the goal of missions like the Habitable Worlds Observatory, a proposed space telescope designed with one explicit purpose. It will use a sophisticated starshade, a giant flower-shaped screen flying tens of thousands of miles in front of the telescope to perfectly block the light of a star. With that blinding glare removed, the faint glow of orbiting planets will emerge from the shadows. For the first time, we could get a pixelated image of a pale blue dot around another sun, and take its atmospheric spectrum to hunt for the undeniable signs of oxygen, water, and methane. Even more advanced concepts, using fleets of telescopes flying in formation as an interferometer, could one day map the continents and clouds of these alien worlds. This gathering data will paint targets on our galactic map, and some visionaries are already planning the ultimate journey. The Breakthrough Starshot Initiative is a bold, long-term concept to send a fleet of tiny, gram-weight probes to our nearest stellar neighbor, the Proxima Centauri system. Propelled by powerful Earth-based lasers pushing on light sails, these nanocraft could theoretically reach 20% the speed of light, making the 4-light-year journey in just about 20 years. Upon arrival, they would scream past any planets, snapping a handful of images and collecting data in a blinding flash before racing on into the void. It is a staggering technical challenge, but it represents a fundamental shift in thinking. We are no longer content to just look. We are beginning to dream of how to touch these other worlds, to send our own silent messengers into the cosmic ocean we have spent so long merely gazing upon. The planets we have listed today are not just entries in a catalogue, they are destinations. From scorching super-Earths to dark, globe-spanning oceans, these 30 worlds represent the breathtaking breadth of possibility in our galaxy. We have journeyed past rocky twins basking in red dwarf twilight and sailed the imagined seas of Hycean giants, each discovery a single, precious data point in a search spanning the cosmos. Every new world we add to this map, from the serene calm of Ross 128b to the chemical mysteries of K218b, brings us one step closer to answering the question that has haunted humanity since we first looked up. Are we alone? The silence is not empty. It is filled with the quiet orbits of these candidate worlds, each a potential home waiting to be understood. The next time you gaze at the night sky, remember that those points of light are not just stars. They are suns, and around them may circle planets with crimson sunsets, triple star dawns, or deep, hidden seas. Our search has only just begun, and the greatest discovery in history might be waiting in the data of our next great telescope. Which of these 30 worlds do you think holds the secret? Let us know in the comments, and if you want to join us on more journeys to the edge of understanding, be sure to subscribe. The universe is full of mysteries, and our map to them grows more detailed every single day.